Good morning and welcome to this Conservation Applied Research and Development, or CARD webinar. Thanks so much for joining today. We hope that you and your families are safe and healthy during COVID pandemic and that everyone is adapting well to the evolving situation. Also, we want to thank you in advance for your patience with any technical difficulties we might have related to the fact that all of our presenters are connected remotely. I'm Mary Sue Lobenstein, the R&D Program Administrator at the Minnesota Department of Commerce, Division of Energy Resources. With me today is Lindsay Anderson, State Program Administrator at the Department of Commerce. At the department, Lindsay provides project development, support, program evaluation, and public information coordination for programs related to statewide industrial, commercial, and residential building energy efficiency, as well as for energy assurance. Lindsay is a project manager for this CARD project and will be handling the Q&A portion of the webinar. Our presenters today are Jeanette Lazaks and Tinyao Zhang from Slipstream and Becky Alexander from LHB. As a senior researcher at Slipstream, Jeanette's work focuses on developing and managing residential and commercial energy efficiency research and planning projects. She applies technical research to examine how people use energy and combines skills in billing analysis, planning, and econometrics. To identify energy impacts and opportunities. In addition to her work at Slipstream, she serves as a co-chair on the City of Madison's Sustainable Madison Commission. Tianyao is an energy engineer at Slipstream, where she consults with building owners, architects, and engineers to identify and recommend energy conservation measures in commercial buildings. In addition, Tianyao conducts research on new energy efficiency technologies, market characterization studies, and commercial energy code compliance assessments. As an architect and researcher at LHB, Becky does a combination of sustainable building research and architectural design. Her research involves collecting, analyzing, visualizing, and synthesizing data at building, organization, and citywide scales. She is on the management team for the state of Minnesota's B3 and SB 2030 programs, where she tracks performance metrics and sustainable strategies of state-funded buildings through her work managing the online B3 case studies database. And we're very fortunate to have all three presenters on our webinar today. Before we start, I'd like to go over a few items for those viewing online so you know how to participate in today's webinar. Each of you should see a control panel somewhere on your screen. The location of that will depend on whether you're using your phone or your computer. If you're using your computer, you can expand and collapse the panel by clicking on an orange arrow. Also, please be sure to maximize your screen for the best viewing experience. By default, you have joined the presentation using your computer speaker system. If you would prefer to join over the telephone, just select phone call and the audio panel of the control panel in the dial will provide dial-in information. All attendees have joined the webinar with their audio muted. If you are having any sound issues, please head up to the audio tab and click on the sound check. That usually resolves any issues. If that doesn't work, try switching between phone or computer call-in. If you are still having problems, try closing out of the GoToWebinar web pane and the webinar completely and then re-entering. You can submit questions to our presenters at any time using the questions panel. Simply type your question and submit it. If there are questions we are unable to answer, we will follow up with you after the webinar. This webinar is being recorded and the recording will be available at a later date on both the department's and Slipstream's websites. A copy of the slide deck for today's presentation is also available as a handout in your GoToWebinar panel, which you can download at any time. This webinar is one in an ongoing series designed to summarize the results from research projects funded by Minnesota's Applied Research and Development Fund, which was established in the Next Generation Energy Act of 2007. The purpose of the fund is to help Minnesota utilities achieve their energy savings goal. $2.6 million of this fund is set aside annually for the CARD program, which awards research grants in a competitive request for proposal process. Results from CARD projects provide utilities with data to enhance energy efficiency program designs within their SIP portfolios. As you can see by this pie chart, CARD projects funded to date have been in all building sectors, as well as some that cross all or multiple sectors. The subject of today's webinar is in the commercial sector and examines a study which characterizes the energy code elements of 78 commercial buildings that are under construction or newly constructed in Minnesota. Now I'm going to turn it over to Jeanette for today's presentation.
All right, thank you, Mary Sue, for that great introduction and background. And thank you for the Department of Commerce for funding this research. We are excited to talk to you today about the results of this new commercial building baseline study, a project that's over 2 years in the making. This project wouldn't have been possible without the hard work of many people, so I wanted to express my appreciation for our research partners, including my own colleagues at Slipstream, LHB, Franklin Energy, and Institute for Market Transformation. So here's what we'll cover today, and we'd like to leave plenty of time for questions, so I will dive right in and start with a bit of background on our study and our approach. Now, to make sure we are all on the same page, and especially since Minnesota has recently adopted a new commercial building energy code as of March of this year, 2020, I want to point out that this study is based on commercial building code adopted in 2015, with the energy portion based on IECC 2012 and ASHRAE standard 90.1 2010. As you can see here, for each code path, there are two options, a prescriptive path and a performance path, which involves energy modeling. But let's start with a pretty basic question here. Why is it even important to study building energy codes? Well, they can be an effective tool to improve building energy performance. However, they are only as effective as the rate of compliance with them. Some states try to capture some of the lost savings from not complying with code through utility energy programming that provides training review or design support. And Minnesota has the policy mechanism to implement such a program, but the potential for energy savings or for additional savings hasn't been quantified with recent codes and recent industry activity. So to address that knowledge gap, we had three overarching goals for this research. The first, to characterize the energy efficiency in Minnesota for new and renovated buildings using methods that could be extrapolated to the greater statewide population. We also identified specific opportunities for increased energy savings through existing commercial building energy codes, and also to identify opportunities for measures that go beyond commercial energy code requirements, and with recommendations including, but not necessarily limited to, existing or new utility conservation improvement programs. Before getting too far, I do want to mention that the methods in the study build upon other code compliance studies conducted throughout the country. We are not code officials deciding whether a building complied with building energy code or not, but rather this is a study of lost savings relative to prescriptive code. And when I say lost savings, I mean the energy savings that are left on the table from not meeting code. So let's get into some of the details about our approach. At the outset of the project, we needed to decide which building segments to include in our study design. We wanted to choose segments that may have the greatest energy impacts for the state. And we utilized data purchased from Dodge Data, it's a commercial construction database firm, to do a preliminary analysis of the market in Minnesota. Linking that data to the Department of Energy's CBEX, or the Commercial Building Energy Consumption Survey, we were able to estimate the relative rank of building types in the Minnesota market weighted by energy intensity. And this is the chart you see here. And those yellow bars reflect the building types that we ultimately chose to be in our study. So we stratified our sample, we divided our sample into four main categories: high-rise multifamily, office, food service and retail, and a fourth category, education and other, which is somewhat of a catch-all for public assembly, public order, religious facilities, and other buildings. These groupings, I should note, are driven largely by similarities in code elements in each building type. And also, based on that initial Dodge data research, we decided to stratify based on size for all categories except for food service and retail. So the small buildings would be less than 100,000 square feet, and large buildings would be greater than or equal to 100,000 square feet. Ultimately, we were able to recruit and gather data for 78 projects in Minnesota, and those projects are shown here on the map to the right. So our protocols and processes were based on experiences of other studies implemented throughout the country, which we adapted to our own study framework. So we started by recruiting through cold calls through this random sample of Dodge data projects. Now, after realizing this process was really time consuming and reflecting on similar experiences of other code compliance studies, we shifted to relying on existing industry networks using the Dodge dataset as a starting point. And once that project was recruited, we reviewed the design and construction documents to identify whether a code element was complied with in the plans. One challenge we found during this review process was that not all projects clearly documented that compliance path the project was taking. For example, whether they're going down IACC 2012 or the ASHRAE 90.1 path. Knowing that compliance path is important for this research, but also, as we'll discuss later, for code officials, especially to know what requirements to follow for various code elements. So for those projects where we lacked that information about code path, we made some assumptions about code elements and requirements to include. Now, the next step was during our site visit, our field staff worked to verify the condition as expected from the plan review, even though the timing of the site visit didn't necessarily align with all code elements being available for confirmation. For example, we couldn't confirm an efficiency of a piece of equipment if we went on the site visit before all the HVAC was installed. However, our goal was not to capture every site visit at the perfect time, but rather to observe each individual code element in enough total sites. The buildings in our sample spanned a range of construction timeframes, such that nearly all code elements were able to be verified for some portion of the buildings. And finally, all the data was input into our analytical tool, which we could calculate loss savings. And here is the screenshot of that tool. It served as our analytical engine for this work. This spreadsheet was originally developed by the Pacific Northwest National Lab, PNNL, and it was updated by our project team to adjust to the study's building segments that I mentioned and the Minnesota climate zones, as well as we added some code elements. So we input all data collected in the plan review and in the site verification visit into the spreadsheet that ultimately calculates the loss energy and cost savings between baseline and proposed conditions for each code element based on a regression analysis model. So there's plenty more detail on our study approach and methods in the reports, but to keep us moving forward, we will dive right into the results. I'm going to start with a few key takeaways first, and then we'll get into details over the next number of slides. Overall, we found that there were substantial loss savings for meeting code. In other words, we found that commercial building market was leaving energy savings on the table by not building exactly to prescriptive code. So we identified some trends of where those loss savings were most likely to be found. For example, envelope measures were more likely to be complied with, while mechanical code elements, specifically those around control and configuration elements, were most likely not to be complied with. And we did find several code elements commonly going beyond prescriptive code already. And we'll talk through some of those in more detail and explain how we use that information to inform our estimates for beyond code potential. So let's take a look at an overview of the results. And first, let me walk you through this chart that we're looking at here. So those blue dots with the error bars show the mean compliance rate, the average compliance rate by building, with the values on the right side axis. The green bars show the loss savings estimate per 1,000 square feet. And it's normalized by square feet so that it's more easily compared across building segments. So what we see here is an average compliance rate of somewhere between 70 and 85%. And put in another way, if the Minnesota commercial building market were to fully meet energy code requirements for just 1 year of construction, it would provide over $10 million in annual loss savings. Now, a couple things to point out, small high-rise multifamily on the left and both small and large education and other building segments on the right show a higher level of energy compliance when compared to others. There are quite a few reasons that potentially go into these differences, and we'll walk through some in this presentation later. But generally, we found that design documents that were available to us were more complete for those building segments compared to food service and retail and office, which may be contributing to the higher compliance rate. Additionally, since multifamily buildings operate 24/7, code elements including thermostat setbacks or exterior lighting controls, those aren't applicable. And even those code elements commonly showed lower compliance rates in other building types. So you'll probably notice that tall bar of the food service retail segment for lost savings per square foot, which shows a lower compliance rate also. I do want to mention a couple things that might be driving this. For one, recruitment was a challenge for these buildings. We only had 6 projects in our sample of 78 buildings. We also found that the projects in our study of these 6 projects, had unique choices for building design that affect energy code elements for which we would have expected higher compliance rates based on our experience. I won't get into those details now. The report has more information, but I wanted to point that out. And then finally, speaking of small sample size, that large office segment only had 1 project, again, due to recruitment challenges. So those results need to be taken with caution, and that's the reason why you don't see any error bars around the point estimate there. So we break down our results further to understand the variations between energy code elements by their end use. So let me walk you through this graph now. At the bottom are the building segments, and each one of those is broken out by end use, either envelope, lighting, electrical, and mechanical and plumbing. And this is where we generally see that the envelope code elements tend to be more complied with more often than the mechanical and plumbing elements and the lighting and electrical elements. Although the error bars suggest that for some building segments, the differences aren't statistically significant. So mechanical code elements generally yielded the lowest compliance rate, and much of the non-compliance in this category comes from control and configuration elements, as I mentioned before, but as opposed to equipment or hardware. And this is a great segue to pass it over to Nyao, who will talk through some additional details about individual measures that are driving our overall results.
Thank you, Jeanette. Let's take a look at the top worst performing elements in mechanical and plumbing end use. This chart shows code elements where we often saw non-compliance. The horizontal bars signify the total annual loss savings, broken out by fuel. Electricity is blue and natural gas is green. The percentages at the end of the bars show compliance rates for that measure across all building segments. What I'd like to emphasize here is that overall, like Jeanette mentioned, the lost savings predominantly result from control elements rather than equipment efficiency. The market for HVAC equipment has shifted enough that commonly available product lines already meet code efficiency ratings. For controls, on the other hand, many settings and sequences are still programmed manually during installation, making them prone to error, especially when the sequence of operations is not well documented. The top 2 worst performing elements that we found in the field are related to HVAC thermostat control, which are deadband and heating setback. Thermostat deadband is the temperature difference between cooling and heating set points, and code requires a minimum 5-degree difference. In drawings, this was not often documented. In some cases, we found that it was documented, but with non-compliant values. In the field, we observed non-compliance in many instances. This picture here is one example, which shows a deadband of only 2 degrees. While both the thermostat deadband and heating setback are largely controlled by the occupants, having this documented in the plans and sequence of operations may help contractors with their initial setup and using code-compliant values as defaults, instead of leaving the thermostats at a random setting. The HVAC fan power element has a high energy impact, especially if building operation hours and corresponding fan run hours are long. This element requires HVAC fan energy to not exceed the code maximum power. It requires the design team to conduct a supplemental fan power calculation, which is moderately complex, though fan selection software can aid in this calculation. Whether or not this calculation is always performed it is rarely documented in the drawings, making this more difficult for the code official to evaluate compliance. When the calculation is not performed, it adds risk for non-compliance. Mechanical commissioning is critical in ensuring that the system is operating at optimal conditions and with the proper control sequences. Commissioning can have a significant impact on energy consumption in just about any size of building. We found there was often a lack of a commissioning plan, which suggests that commissioning was not planned for in the design and not carried out in the field. In a few cases, mechanical commissioning was included in the design specifications, but ultimately removed during construction due to building owners' concern about cost. In the interest of time, I won't get into the other mechanical elements now, but the report will have additional details. But I do want to highlight some mechanical code elements that we found to be commonly complied with. Like I mentioned before, this includes cooling and heating equipment efficiency. The chart on the right here shows an example of where we saw cooling efficiency meeting or exceeding minimum code baseline. On the y-axis, we have the air conditioner cooling efficiency in SEER unit. Each data point represents an instance, and we have the horizontal line representing code minimum efficiency of 13 SEER. Most of those points are either at code baseline or well above, signifying a performance greater than code. Efficient equipment for all system types is commonly available on the market, which simplifies the process of equipment selection and ensuring code compliance. We also saw high levels of compliance in the presence of air economizers and pipe insulation for space heating and domestic hot water, and finally, duct insulation. Here we have an example of a building automation system screenshot showing a diagram of a VAV air handling unit at current operating conditions, demonstrating a number of code elements that are being complied with. First, we see that the economizer is present and active, and also the unit controls include optimal start, supplier temperature reset, and static pressure reset capabilities. Minimum outside air is brought in through ERU-1, and the name suggests that it is an energy recovery unit. The heating setback is also noted here. In general, facilities with a building automation system makes it easier for code officials to verify operating conditions. However, if the facility does not have a BAS, it is much harder for on-site verification. That puts emphasis on plan documentation, which is in general very important, but even more so for mechanical code elements when a BAS is not in the design. I won't spend as much time on our lighting and electrical code elements, except to point out here that all of the code elements that we saw, significant loss savings, involved controls or commissioning. Receptacle control was one of the least compliant electrical code elements and applicable to half of the buildings in the study. ASHRAE 90.1 2010 requires at least 50% of all receptacles installed in private offices, open offices, and computer classrooms be controlled by an automatic control device that functions on a schedule or occupancy sensors. This element is often not documented well on electrical drawings. As this is a relatively straightforward hardware component, it would seem that many design teams are either unaware of the receptacle control requirement or have chosen not to comply. In comparison to mechanical commissioning, lighting testing and commissioning appears to be even less widely implemented. This may be because it is a newer practice, given that advanced controls are newer to the industry. However, the energy impact can be significant, as lighting is still one of the highest energy consumers in commercial buildings. Documentation of a lighting commissioning plan is lacking in many instances, which suggests that it was not planned for during design and not carried out in the field. In a few cases, lighting commissioning was included in the design specifications, but ultimately removed during construction due to building owners' concern about cost. And here's a similar graphic for envelope code elements. Like we mentioned before, envelope elements tend to be more complied with than other code elements. I want to point out some trends that we saw on the 4 code elements shown here. Fenestration orientation requires the building to have more window area on the south facade than either the west facade or east facade. to maximize solar heat gain benefits. Here we see relatively low compliance rates at around 34% and a significant amount of lost savings compared to other envelope code elements. Meeting this element can be difficult for buildings that are designed to be longer in the north-south axis, but we found that non-compliance occurred in all building footprints. This code element is relatively easy to evaluate during design and should be addressed by code officials and designers at that time. The non-compliance for window properties, such as solar heat gain coefficient and U factor, was most likely found in custom-built glazing, such as storefront and curtain wall glazing. Fenestration performance needs to be specified as a full assembly, with both the glazing and the frame, which rarely happens. This is a common point of confusion in the building design and construction industry, as in many cases, the glass performance values are reported without consideration for the frame, because glass-only performance is easy to identify and report. Full assembly performance requires an independent analysis on most projects. This analysis is often conducted or available, but not communicated to key design team members and code officials. When it is communicated, it is often not in a timely manner. Unfortunately, most frames significantly degrade overall performance, so this practice needs to improve. The window-to-wall ratio element had a higher compliance rate than other fenestration elements, but there were a few instances of non-compliance where the amount of glazing exceeds code limits. This element has a large energy impact, so even small amounts of non-compliance can add up to substantial lost savings. Now I want to shift gears slightly and touch on the importance of plan documentation. Plan documentation has the potential to affect whether a building is designed to energy code, because it is by definition the method to convey to construction teams what is to be built. If an element is poorly documented in the plans and specifications, there is risk for confusion in how the building actually gets built. Any compliance found in the field is either accidental or due to a contractor's prior knowledge of the code. Here we show examples of drawings that detail how the project plans to meet code. Now we like to point to common non-compliant elements that were poorly documented in plans and specifications. We see similar trends of controls and commissioning being code elements that tend to be poorly documented. Most elements shown here had appeared a couple slides up in the worst performance list, which stress the importance that plan documentation may play to meet building energy code. In addition to these poorly documented elements not built to code, we also saw cases of code elements that were well documented, just not to code minimum requirements, such as exterior lighting control. The report has more details on those elements. Now, as we mentioned before, our research showed multiple instances where projects are designing above and beyond code requirements. To assess the potential energy savings for Minnesota commercial buildings to build beyond code, we modeled a typical building for each of the office, multifamily, and food service and retail segments, and for each energy code element, applied the best case conditions that our study found at any one site in each segment. In determining the best case conditions, we removed outliers that, based on our experience, seemed too unrealistic for most buildings to follow. Applying the same methods as the lost savings calculations and using modeling assumptions based on site data, we calculated total energy savings for each building type using ASHRAE 90.1 2010 prescriptive path as the baseline. Based on the results, we found that mechanical code elements showed significant potential across all three building segments. Here we show a graph that lists the overall potential savings beyond ASHRAE prescriptive code by building segment. The dark blue bar represents envelope end-use elements, green bar represents mechanical and plumbing end-use elements, and the light blue bar represents lighting and electrical end-use elements. From here, we can see that lighting and mechanical elements show the highest potential in energy savings for office and food service and retail. This is primarily due to the nature of these two building types having a higher interior lighting power allowance and higher occupant densities and ventilation loads. While there is less lighting savings opportunities in high-rise multifamily due to lighting control elements not applicable in dwelling units and lighting power savings which can only be claimed for hardwire fixtures and not resident-provided plug-and-play lighting, there is still large potential in mechanical and envelope elements. High-rise multifamily typically has a good amount of glazing area, which provides energy-saving opportunities for low U-value and SUGC windows. We can see here that in addition to the lost savings from code compliance, Minnesota commercial customers has the potential to save another $6 million in energy use by designing above and beyond energy code. Here we show a number of elements that were already going above and beyond code minimum requirements, which include mass wall insulation, interior and exterior lighting power reduction, and HVAC cooling and heating efficiency. The graph shown here is a little different than the previous chart. You'll notice there is no code minimum line because this is a distribution of percent reduction from code for exterior lighting power, which ranges from 5% to as high as 80%. These efficiencies are results of both efficient fixture layout and the use of high-efficacy LED fixtures. As mentioned earlier, we see that equipment cooling and heating efficiency already tends to meet prescriptive code and often goes above and beyond code minimum requirements. The graph shown here is the distribution of hot water boiler thermal efficiencies, which exemplifies how new commercial buildings are already exceeding code minimum thresholds in this one code element. Now, let's shift gears to some of the report's conclusions about opportunities and recommendations. I'll pass it over to Becky Alexander, our research partner at LHB.
Thanks, Tinyao. So as you've heard from Jeanette and Tinyao, our study shows significant energy savings are available both from reaching the full potential of the energy code as well as expanding the implementation of those beyond code opportunities. We've identified opportunities based on our field study results, and we've developed recommendations based on a review of examples from across the country. We won't be digging into these examples in too much detail today, but descriptions are included in the final report for this project. Starting with opportunities for reaching the full potential of the energy code, we've identified 3 areas where an energy code program can provide support. 1, for code officials, 2, for design teams, and 3, specifically for controls documentation and commissioning. So we'll dig into each of those. Starting with support for code officials. We found that there were opportunities for code officials to help achieve additional savings by educating design teams about code requirements, by catching non-compliant and or undocumented code elements during their plan review, and then by verifying commonly non-compliant elements through their on-site inspections. However, we've also heard that code officials often lack the time and the tools they need to enforce these really increasingly complex energy code provisions on top of the many other codes that they're responsible for that also support the health and safety of the public. So to overcome this, we're recommending offering multiple support options, including using both a circuit rider model and offering the services of third-party energy code reviewers. A circuit rider is an individual who can deliver energy code resources and on-call, project-based technical support to code officials. And while these individuals would typically play a supporting role, third-party programs would actually outsource aspects of the energy code plan review, on-site inspections, and or performance testing to a third-party expert. And depending on the needs of the jurisdiction, these programs can either take on all aspects of energy code enforcement, or they can just focus on high impact items that require significant time or expertise. One example of that would be the energy model review for projects using one of the performance pathways of the code. Our study also found that design team support can help increase energy savings by minimizing the number of code elements that are either not specified in the design documents or specified but not meeting energy code requirements. So this would start with making sure that the different code pathways are understood and specified on the documents. As Jeanette alluded to, 33 of the 78 projects in our study did not indicate whether IECC or ASHRAE was used as the code pathway. But support should also be provided for the code elements that Tinyao called out as being commonly missed or misunderstood, whether that's thermostat deadband, the receptacle controls, things like fenestration orientation as well. So our recommendation, based on findings from Minnesota's 2018 Commercial Energy Code Compliance Enhancement Pilot, which was conducted by the Center for Energy and Environment, are to provide design team education through code officials and focus on early design phase meetings and quick reference tools. So the circuit rider model can actually be used to develop a shared set of resources that get shared with code officials who would then pass the information along to design teams. And ideas for resources include a sample agenda for code officials to host early design kickoff meetings with the design teams, where they would discuss energy code requirements, the different options for compliance paths, and potential project challenges that are a little bit more project specific. And this was one of the successful tools that was tested in CEE's pilot. In addition, phase-specific checklists could be provided that highlight code elements with the greatest energy impact and enable the users to really easily identify energy code requirements that are applicable to their project, to track energy code compliance throughout the design process, and to identify the documentation requirements. So we're not seeing as many examples like Tanya identified of undocumented code elements. And this could even be something, these checklists could be something that gets submitted to the code official to assist with plan review and site inspection. Finally, our study found that non-compliance with control code elements and commissioning contributed to over 3/4 of the total lost energy savings. And again, this was primarily due to a lack of clear documentation. So to address this, we're recommending increasing commissioning compliance by providing education to owners about the value of commissioning, making sure it's not value engineered out during construction, providing owners, project teams, and commissioning agents with more clear guidance on the commissioning expectations for their project. And this can be especially helpful given the significant differences in the commissioning requirements of IECC versus ASHRAE. And it's also something that Washington State, California, and Austin, Texas have each implemented. And then finally, supporting the enforcement of controls through plan review to make sure that there's a well-documented sequence of operations, through on-site spot checks of high-impact items, and through a review of a commissioning checklist. And this is a good example where a third-party expert would be useful due to just the complexity of control sequences and commissioning. So we also took a look at opportunities for beyond code energy savings, since current energy codes aren't getting us far enough to meet our local and global energy and climate goals. Our recommendations for Minnesota are to promote high-impact prescriptive strategies, to promote energy modeling, to address non-regulated design decisions and help projects identify the most cost-effective strategies, and to address operational performance, to both ensure promised savings are delivered and to capture some additional savings from operational and behavioral strategies. So each of these recommendations can either be incorporated into existing or new incentive-based utility programs, or they could be incorporated into the state's energy code, which I'll touch on in the final slide. So going through these in a little bit more detail, starting with prescriptive strategies. Prescriptive strategies are relatively easy to understand and incorporate into construction documents, which makes them a useful tool for projects of all sizes and levels of sophistication. As Tanya described, many projects are already achieving savings beyond prescriptive code requirements. So expanding these market-ready, beyond code elements to additional buildings would be one straightforward way to gain additional energy savings. In addition to these market-ready strategies, prescriptive elements from future code versions could be incentivized, which would help reduce the problem we saw of industry unfamiliarity with these code elements in the future. These types of strategies can be promoted through the new construction programs that are already being offered by utilities around the state and can be done either a la carte for individual strategies and or by offering different tiers or bundles of strategies, which is something that's demonstrated in the advanced building new construction guides that have been developed by the New Buildings Institute, which provide multiple tiers of prescriptive strategies that lead to different levels of savings. Our next recommendation is to promote energy modeling. So as energy goals become more aggressive, the prescriptive approach of maximizing individual building components is expected to soon reach its limits of cost effectiveness. Energy modeling can help holistically identify savings opportunities and inform design decisions that aren't addressed in prescriptive codes, such as the choice of HVAC system. In the 2015 Minnesota Energy Code, there are 2 performance pathways, as Jeanette showed on one of the first slides, that use energy modeling to show compliance. But our study didn't find a single project that used either of these pathways. When we spoke with local and national design professionals, we learned that these pathways may not often be used because of the extra time and cost of meeting the requirements of a verification model, which is occurring too late in the design process to cost effectively impact design. So to fully identify the barriers to using performance-based energy code pathways, we're recommending conducting a more rigorous market analysis of energy modeling practices in Minnesota, which can help inform future program development. We also recommend expanding the reach and function of existing performance-based new construction programs to include early design analysis of non-regulated elements, so things like building massing, orientation, window placement, and HVAC system type. Excel's Energy Design Assistance Enhanced track is one example of this type of program, and we'd recommend expanding these programs to utilities that currently don't offer such a service, as well as working to increase participation by either conducting additional recruiting or easing some of the eligibility requirements. Taking the notion of performance one step further, additional savings can be captured by verifying performance during building operations from actual metered data. And current codes don't extend into this operations phase, so it's difficult to verify whether the savings from code elements like control sequences are being fully realized. In fact, just over a third of the code elements we reviewed are dependent on building operations to achieve ongoing savings. And since building operators are typically most concerned with occupant comfort, there are likely to be lost savings due to operational changes. Our study also found that several high-impact code elements are difficult to confirm through on-site inspections. So for example, fenestration U values are nearly impossible to confirm on-site for custom assemblies, and verifying the continuous air barrier requires reviewing many different detail conditions before they get covered up by the exterior finished material. So programs and code pathways that focus on operational energy use can therefore provide a method for us to ensure that savings from these hard to verify code elements are actually being achieved. So we're recommending implementing a voluntary whole building pay for performance program to reward project savings on an ongoing basis as they occur, which is a shift from the typical model of providing upfront payments to fund energy efficiency strategies. A recent study by CEE found significant potential for energy savings for a pay-for-performance program for commercial construction in Minnesota. Finally, while the recommendations I've been describing are for incentive-based utility programs, we also encourage Minnesota to incorporate these approaches into future code pathways, which is a topic that's currently being explored through a separate CARD-funded project that's developing a roadmap for a statewide codes and standards program. We're recommending that the following options are evaluated. 1, adopting a more aggressive prescriptive and performance-based pathways as the state building energy code. 2, develop a step energy code option for adoption by local jurisdictions with both prescriptive and performance-based pathways. And 3, develop a pilot outcome-based energy code pathway that's using the metered data rather than design documents or energy models to determine if this is an option that would positively impact energy code enforcement, compliance, and energy savings in Minnesota. And based on precedents from Seattle and Boulder, the pilot should evaluate enforcement mechanisms, it should look at energy and financial impacts, and it should collaborate with a diverse set of stakeholders to assess market barriers and opportunities for this type of code pathway. With that, I would like to thank you for listening, and I will turn it back over to Mary Sue before we start our questions.
Great. Thank you very much, Becky. That was a great presentation. If you've not already done so, please type your questions into the Q&A box and send them to us. And Lindsay, do you have any questions in the queue for Jeanette, Tanya, or Becky?
The first question we have is, how does the team balance pay for performance with the fact that payments well after the first cost incurred may not be as influential a decision maker, since the building owner or occupant may change, sometimes not very long after construction is complete?
Great question. I think, Becky, could you take that?
Yeah, I think that in the way that we're considering pay for performance is to help take credit for some of the operational strategies. So things like that thermostat deadband and other control settings, where it's not an extra cost upfront, so you're not needing to pay extra for that. It's just a matter of keeping that consistent throughout operations. So I think you wouldn't have that same conflict that you're talking about between who pays for a strategy versus who gets the rewards for the strategy.
Okay, great. Next question. How feasible is it to build the beyond code potential commercial building statewide based off of the research here in Minnesota?
This is Tanya. That's a great question as well. So when we're looking at the best case scenarios on code elements for each building segment, we did make note to exclude the instances that we thought were just too aggressive to promote statewide. So we focused on items that were best practice while still being feasible. And when we used prototype energy models to calculate the savings potential for each building segment, we purposefully chose fuel sources and HVAC system types that we felt were most common and representative of the Minnesota commercial market, so as to get as realistic as possible in showing savings.
Great, thank you. Next question. How transferable are these study results to the current Minnesota commercial code?
Yeah, so for commercial buildings, ASHRAE 98.1 2016 is roughly 13% better than ASHRAE 98.1 2010, based on DOE determination studies. For our study, we did not go through and compare each code element between those two code cycles. So it is hard to break out the impact for each individual element. However, we do know that HVAC and lighting controls and commissioning are still a big part of the new code, and we would expect to see large savings opportunities there, considering that there might be a lag time for design teams to update their design standards according to the new code.
Okay, thank you. Did you come across any municipalities that have staff that focuses on energy code compliance within their building code staff?
I may be able to take that one, although I think the way our research was developed, we didn't talk to code officials at the city level for our research, and that would be kind of I think that would actually be a really interesting question and should be explored, and it might be being explored in the codes and standards road mapping process, but it's something that was out of our scope. But something I might want to dig into and maybe reach back out to that whoever answered that question with additional information. I don't know if Becky if Becky or Tinyao had anything to add to them on that one.
I think just anecdotally that some cities have code officials that are more familiar with the code elements required by energy code, so they might take on the more complex projects, but from just the limited exposure I've had, that's more common in larger cities than in smaller ones.
Okay, next question. Could you share more about how commission compliance compared between the design phase and the actual implementation? Were you able to confirm the commissioning reports were provided?
So among our 78 projects, we didn't get many commissioning reports. I felt like it was less than 5. In most cases, we verified commissioning just based on the plans and documentation, the specifications, if they did include a section on commissioning, and then we verbally confirmed with the on-site contractor whether or not commissioning was carried out or was planned to be carried out. But we, in most cases, we could not get our hands on the actual commissioning report. So for the plans, we'll be verifying through the specifications, and on-site would be verbal verification.
And this also may be reflective of the timing of the site visit as well, when the commissioning plan may be done later in the construction time frame. And or the person that we're talking to may not be as familiar with how to secure that, so they could send it to us. A great question, though.
Yeah. Did you evaluate whether there was any difference in compliance rates between energy code enforcement and non-enforcement areas?
Yeah, so that's something I didn't bring up in the presentation, but at the outset of the project, we did do an analysis of enforcement areas. For those that may not be familiar, there are the code can be enforced either through the counties or through specific municipalities. We were able to merge basically that Dodge data set that I mentioned before of commercial construction against a GIS map of the code enforcement areas. And what we found from the Dodge data is that only about 5% of the commercial market was in non-enforcement areas. So we chose not to try to stratify based on that, or have any targets for sampling buildings in non-enforcement areas, because that number was too low to get any kind of real results. We would have had to oversample a lot, and at 5% it would have been potentially very difficult to get that information. That said, I think we had 2 projects that were in non-enforcement areas out of the 78. So that actually kind of is consistent with our initial analysis of about 5% being in non-enforcement areas. For those that watched the residential baseline study webinar a couple weeks ago, that was different. They did look at and stratify based on enforcement areas.
Okay. You had mentioned renovations as part of the study scope. How did you approach the renovations within the study?
All right, I'll take that on again. So again, this is me being very brief in our approach. There's more detail about this in the report, but we did also have targets. We didn't stratify. Like I said, we stratified on the 4 segments and the building size. We couldn't feasibly stratify anything further, but we also wanted to make sure that we captured some of the renovation differences, because in that initial Dodge data research, we found that somewhere around 20 to 30%, and I don't have the exact number off the top of my head, were renovations based on the Dodge data classification. So we wanted to make sure that that renovations were in our scope. The way we dealt with that was largely through recruitment. If a renovation, we had to have like a minimum renovation for it to be included in our project, and what that meant was 2 out of 3 major systems. So it had to have a major HVAC upgrade or envelope upgrade, or lighting upgrade and HVAC, and then it could be included. And we recruited that based on conversations, or we ensured that it met our requirements based on recruitment conversations that we had. And what we ultimately had in our sample were 20 renovated buildings or projects out of the 78. And while I'm talking about that, I should also mention we did a similar thing with climate zones, because Minnesota has 2 climate zones, 6A and 7. Sorry, I think I messed up which one has the A, but basically there's 2 climate zones. We wanted to make sure that that our study sample was reflecting those climate zone differences, and so we also had sampling targets, not necessarily stratifications, but we wanted to try to meet sampling target in those 2 climate zones. And ultimately, we had 12 in our sample from climate zone 7, which is the northern part of Minnesota. Hopefully that answers that.
Yeah. There are 2 more questions that came in that we do have recorded, and we'll answer and send out via email. But at this time, I should transition it back to Mary Sue for wrap up.
Thank you. Thank you very much for those great questions and for the presentation. I'll just mention again that the recording of this webinar and the slide set's available now if you want to download it from your GoToWebinar panel, but the recording and will be available at the department's website in a few weeks, and so will the final report in a few months, and it'll also be available on Slipstream's website. When the final report and webinar recording are available, you can link to either of them from our Applied Research and Development webpage. Can you go to the next slide, please? Which is indicated on this slide, a copy, so there. Then this webinar page has other additional resources and information that's related to the CARD program and to CARD research projects that you might want to check out. And the address is at the bottom of this slide. At the end of this webinar, there's an evaluation that will pop up. So please take the time to fill that out. It will be very helpful in trying to help us think about these projects in the future. And thanks again for participating. We really appreciate your interest in CARD projects. Before we leave, I do want to take the opportunity to mention some upcoming CARD webinars. The first will report on results from a study that looked at opportunities to reduce light levels in Minnesota commercial buildings and is conducted again by Slipstream. That one is on September 29th. On October 20th, the Center for Energy and Environment will discuss findings from their investigation of dehumidification in Minnesota single-family homes. And this is standalone dehumidification, portable dehumidification. Then the third project, also presented again by Slipstream, will shed light on the potential for saving energy and carbon emissions with load shifting measures. You can keep abreast of upcoming webinars and other news related to the Conservation Improvement Program by signing up for SIP updates on our email list. You can use the link on this particular slide to do that. But in the meantime, if you have any questions, feel free to contact me. Also with feedback or suggestions for the CARD program or CARD webinars, I'd be delighted to hear from you about any of that. So thanks again, and hope that you and your families will continue to be healthy. So have a good afternoon, and thanks for participating today.